I want to show you how to do a slightly more sophisticated centripetal force problem, and this one's a classic. This is the one where there's a mass tied to a string, and that string is secured to the ceiling, and the mass has been given an initial velocity so that it swings around in a horizontal circle. So this mass is going to maintain a constant height. It's not moving up or down, but it revolves in a horizontal circle. So if you were to view this thing from above or below, it'd look something like this. You'd see the ball tracing out a perfect circle if you were looking at this from right below. And the question I want to ask is two things. What is the tension in the rope? And what has to be the speed of the mass? And these are our given variables. We know the mass is 3 kilograms. We know the length of the rope is 2 meters, and this rope is making an angle of 30 degrees with respect to this vertical line right here. Now this problem's a classic for good reason. If you don't have a clean conceptual understanding of what we really mean by the terms when dealing with centripetal forces, and if you don't have a problem-solving strategy to use to tackle problems, this problem will expose you. So that's why we should go over this, to make sure you have a clean understanding of exactly what we mean by all the different terms, and to show you that there's a strategy you could use to solve any centripetal force problem. And that strategy is this. First, draw a quality force diagram for the object or objects in your problem. So let's do that first. The forces that are acting on this 3 kilogram sphere are the force of gravity. You'll have a force of gravity straight down. That's going to be m times g. So the way we find the force of gravity is with the formula mass times 9.8. And the only other object that's touching this mass is the rope. So the only other force on this mass is the force of tension. So I'm going to label that force with a capital T. This will be the total force of tension from the rope. And really the only other step in this problem solving strategy, it's really only 2 steps, use Newton's second law, but only use it for one direction at a time. And we typically only have 2 directions. I mean, we've got this vertical direction or we've got this horizontal direction. We got a 50-50 shot. I mean, we got to pick one of the 2. It's not like you can pick the wrong direction. If you pick the wrong direction, it'll just mean that you can't solve because there'll be too many variables. But what you write down in that process is probably going to be useful later in the problem anyway, so don't erase it if you pick a direction that you can't solve since you have too many variables. Just go to the other direction and pick that direction. I know what direction to pick because I've done this one before, but if you don't know, the worst thing you can do is freeze up. You got to try something, and if you try the wrong direction, no big deal. There's only one other direction to pick. So I'm going to choose to analyze these forces in the vertical direction. So I'm going to say that the acceleration in the vertical direction, this y direction, is equal to the net force in the y direction divided by the mass. And now I simply ask myself, what is the acceleration in the vertical direction? It's not 9.8. A lot of people want to say negative 9.8, but that's only if this ball were free falling, and this ball is not free falling. In fact, this ball's not even changing its vertical height. It's remaining at the same constant height, and that means not only is there no vertical velocity, there's no vertical acceleration, since the ball's not even moving vertically. So on the left-hand side here, this is great. We could put a 0. Zeros are wonderful. They make calculations easier. So this is going to equal the net force in the vertical direction. So one force is going to be the force of gravity. So I'll put that in here. You'll have m times g. That force is definitely a vertical force, but you got to be careful. If we're going to consider upward as positive, this mg is a negative force. So in terms of y-directed forces, downward, typically the convention is that you choose that to be negative. So I'm going to say that mg is negative. And now we ask ourselves, are there any other vertical forces? Well, we just look at our force diagram. So our force diagram will tell us if there's any other vertical forces. We look over here. The only other force is this tension force. And part of this tension force is vertical. We can't put in the entire tension into this formula. We could only do that if this tension was directed vertically upward. But it's not. Part of it's vertically upward and part of it's horizontal. So part of this tension force is directed this way. I'm going to call that the x component of the tension. And then part of this tension is directed vertically. I'll call that the y component of the tension. So we can only plug in this y component of tension into this formula over here, since we're only plugging in y-directed forces into this equation. So I could just write plus ty, but I don't want to do that. I want to solve for what t is, not what ty is. So I want to write this ty in terms of t. And I can do that. Look at the triangle this is making. This tension and this ty is going to make an angle right here, and that angle has to be the same angle that the rope makes with this vertical line. So the tension is not the rope. The tension is a force exerted by the rope, and the tension lies along the same direction as the rope, but the tension is not the rope. This is a really common misconception. Sometimes people think, oh, the tension is 2 meters, right? No. That's not even a force. That's the length of the rope. And yes, the length of the rope lies along the same direction as the tension force, but the tension is different from the length of the rope. However, this angle between the tension and this vertical component of the tension is the same as the angle between this rope and the vertical direction. So that means we can label this as 30 degrees right here. And now I can figure out what is the vertical component of the tension in terms of T and in terms of theta. I got a right triangle. Here's a right angle. This side that I want to find out, Ty, is adjacent to this 30 degrees. Since it's adjacent, we're going to use cosine. In other words, we're going to say that cosine of theta equals adjacent over hypotenuse. People get confused sometimes. They're like, wait, I thought vertical was always the opposite side. It'd be the opposite side if we knew this angle, but we don't know that angle. We know this vertical angle, and that means this vertical side is adjacent to that angle. So we know the angle. We could write that cosine of 30 degrees is going to equal the adjacent side, and the adjacent side is Ty, and the hypotenuse is going to be T. People get freaked out here. They're like, I've got too many variables, but that's okay. We can label this total hypotenuse as T. Even though we don't know it, it's all right. We're going to manipulate symbols, and we're going to solve for Ty. If I multiply both sides by T, I get that Ty, the vertical component of the tension, is equal to the total tension times cosine of 30 degrees. This is the vertical component of the tension, and this is the force that I can plug into my vertical net force. So I'm going to add, because this points upward, T, the total tension, times cosine of 30. And then I have to divide by my mass. So I can solve this for T now. If I multiply both sides by m times 0 is going to be 0. I'll move the mg over, and then I divide by cosine of 30. I get that the tension in the rope is going to equal mg, the force of gravity, divided by cosine of 30. And if we plug in numbers, we'll get that T equals, the mass was 3 kilograms, g is always 9.8, divided by cosine of 30, gives us a tension of about 33.9 newtons. I'll just say that that's 34 newtons. So that's the tension in the rope. That's the first thing we wanted to find. We just found it over here. That is the tension in the rope. So let's do the next part. Let's try to find the speed. People get a little concerned now. They're like, what do I do? Don't deviate from the plan. We drew our force diagram. We used Newton's second law for one of the directions. You still got work to do? Then do Newton's second law for another direction. We're just going to do this for the x direction. So we'll do the x direction. I'll say that the acceleration in the x direction equals the net force in the x direction divided by the mass. And I'll ask myself the same question. Is there any acceleration in the x direction? There wasn't any acceleration in the y direction. You might think there's not any in the x direction, but there is. This mass is going in a circle. That means there's going to be centripetal acceleration in this direction. So this horizontal direction is essentially just the centripetal direction. So to make that more clear, I'm just going to put AC and FC. And whenever you have centripetal acceleration, we can replace that with v squared, the speed squared, divided by the radius. And that's going to equal the net centripetal force over the mass. What force is acting in the centripetal direction? Well, you can figure that out. It's just the force that was acting in the x direction, because this is the x direction. The x direction is the direction that happens to be pointing toward the center of the circle. That's why the x direction here is just the centripetal direction. So to figure out which forces are centripetal, I just look at my force diagram. I drew this for a reason. I drew this so when I look at it, I can figure out what forces are vertical to put in over here and what forces are centripetal, i.e. horizontal, to put in over here. The only force that's horizontal is the horizontal component of the tension. That's this Tx. But again, instead of just plugging in Tx, we'll plug in what this component is in terms of the angle and the total tension, just like we did over here. Ty was T cosine 30, so it might not be that big of a surprise that Tx, the horizontal component, is just going to be T sine 30. And if you don't believe that, you can prove it to yourself. Think about it. This Tx component is the opposite to this angle. And for opposite, we'll use sine. So we could say that sine of 30 would be the x component, which is the opposite side, over the hypotenuse, which is t. And if you solve this for tx, you multiply both sides by t, you indeed get that tx is just T, the total tension, times sine 30. So we could plug that back in over here. We know that the only component that's acting as a centripetal force, i.e. that's pointing toward the center of the circle, is this x component, which we just found is T sine 30 degrees. Now you see why picking this direction first wouldn't have allowed us to solve, because we wouldn't have known the speed v and we wouldn't have known the tension T. Only because we chose the y direction first, we were able to find the tension, and now that we know this tension being 34 newtons, we could plug that in over here and solve for our speed. But there's a really common mistake that people make here. People really want to plug in r as 2 meters because they're like, hey, you gave me 2 meters over here, I'm going to use it. That's an r, right? Isn't that r? No, that is not r. R here, always in the centripetal formula for the acceleration, this r represents the radius of the circle that the object is moving in. And this object doesn't move in a circle with a radius of 2. The radius of the circle this object's traveling in looks like this. That's the radius of the circle. And that's not 2 meters. How do we find that? We'll again use trigonometry. We're just going to say that we've got a right triangle. This time though, we're going to make a right triangle out of the length, not of the force, not of this tension. We're making a right triangle out of the length. But again, we know that that side's a right angle. We know that this side's 30 degrees. So we can say that this radius is the opposite side of that 30 degrees. So we're going to use sine theta. We're going to say that sine of theta, which is 30, equals the opposite side, and that's r, divided by the total length of the string, L. And so if I solve this for the radius, I get the radius of the circle that this ball is traveling in would be L times sine of 30, where L would be this 2 meters. So we'll plug that in back over here. We'll say that v squared divided by r, which is L sine 30, is going to equal t sine 30 divided by the mass. And now we can solve, we can multiply both sides by L sine 30, and we'd get that v squared is going to equal t sine 30 times L sine 30 divided by the mass of the sphere. And since I want to find v, not v squared, I'll take a square root of both sides. And when I take a square root of both sides, I end up with v is the square root of t sine 30, L sine 30 over the mass. So if we plug in our numbers, we get that v is the square root of t, which is 34 newtons, times sine of 30, times L, and this L is referring to this total length, this 2 meters, times sine of 30, all divided by the mass, which was 3 kilograms. Which if you solve gives you a speed of about 2.38, so I'll just say 2.4 meters per second, which is the speed that we were trying to find. So recapping, when you're solving a sophisticated centripetal force problem, be sure to draw a quality force diagram, then use Newton's second law for a single direction, and only plug forces in that direction into the net force. If the direction you choose happens to lie along the centripetal direction, i.e. it points toward the center of the circle, then you could use v squared over r for your centripetal acceleration. But again, only plug in forces that lie along that direction for the centripetal force. And make sure that you understand when we say the radius, we're talking about the radius of the circle that the object is traveling in.